Welcome to lecture on effective stress. This is the part 2 lecture and a continuation of the effective stress which we did in the previous lecture. So, in the previous lecture we have introduced the concept of effective stress and we said that total stress is equal to effective stress plus pore water pressure, and this is an important equation in geotechnical engineering. So, in this lecture we will look into the much more details of this concept of effective stress, and then we will try to look the effect of fluctuation of water table on the effective stress, what will happen if the water table rises within the ground level, and what will happen if the water level depletes within the ground level, or if the water table rises above the ground level, what will it affect the effective stress or not. We will try to look into this concept in the form of some example problems. Finally, we will try to look the another name of pore water pressure, which is called neutral stress. So, as we introduced in the previous class, like effective stress principle which was put forwarded by Carl Terzaghi in 1936 happens to be the very important equation in geotechnical engineering. This is valid only for saturated soils. Here we can define the effective stress sigma dash at a point in a soil mass is equal to the total stress sigma at that point minus the pore water pressure U at that location. So, here sigma dash is equal to sigma minus UW, and we also discussed that how to determine sigma, that is total stress, in case of homogeneous soils as well as some stratified soil deposits, and UW is the pore water pressure. So, both total stress sigma and pore water pressure U or UW are physically meaningful parameters, and these are the stresses that can be actually measured in the field. So, here we define sigma dash is equal to sigma minus UW. Sigma is the total stress which may be a result of the overburden or the soil above that particular point under consideration, and UW is the pore water pressure, varies from the top of the water surface to the point under consideration. So, both total stress sigma and pore water pressure U are physically meaningful parameters and stresses that can be measured in the field. That is one thing which we should note, is that total stress and pore water pressure are the physically meaningful parameters in the sense that they can be measured in the field. Whereas, in this slide, once again we are trying to look into it to give the importance of the equation proposed by Terzaghi. So, Terzaghi in 1936 proposed the relationship for effective stress. It was said here all measurable effects of a change of stress such as compression, distortion and a change of shearing resistance are due to changes in effective stress, which is now this effective stress is computed mathematically from the total stress and pore water pressure. So, certain aspect of the engineering behavior of soil, especially compression and shear strength of soil, are functions of effective stress. So, if you look into this, certain aspects of engineering behavior of soil like compression and shear strength are the functions of this effective stress. If any change in effective stress, it affects this shear strength characteristics as well as the compression characteristics of a soil. So, first important equation in geotechnical engineering. So, Terzaghi's effective stress principle we have introduced, and then we are now looking into the much more details about this concept of effective stress. So, effective stress sigma dash by definition can be determined only by arithmetic manipulation, that is sigma dash is equal to sigma minus UW. Unlike total stress sigma and pore water pressure UW, sigma dash is thus not a physical parameter. So, one thing which we should remember, unlike total stress and pore water pressure, sigma dash is not a physical parameter. So, it is thus only a mathematical concept, but obviously useful parameter since it has empirically been observed to be determinant of the engineering behavior of the soil. So, though it is a mathematical concept, which is obtained by arithmetic manipulation from total stress and pore water pressure, but as it is determinant to many engineering behavior of the engineering properties of the soil. So, this particular parameter is very important parameter in soil mechanics. So, let us consider now this effective stress concept through idealized saturated soil mass. So, here under certain stress. So, here in this slide grains which are shown here and covered with water, that indicates that all the voids within the grains are filled by water, and A dash and A dash is the wavy plane passes through the contact points of the grains, and this A dash and A dash plane can also passes through the pore water pressure. So, if you see here at this particular points where in this particular place where the contact is very less, so this A dash and A dash is passing through these contact points. So, this is the pore water and these are the grains, sigma is the total stress applied to this. So, this is an idealized saturated soil element in equilibrium. So, what you are seeing, an idealized soil element in equilibrium. Assume, let us consider that this A dash and A dash wavy plane is stretched and made something like A dash and A dash, a plane passing through pore water as well as passing through some grains also. This is an imaginary plane passing through solid grains as well as passing through pore water. So, if that area is imaginary plane is having say area, and if this total stress is acting over that imaginary area A, so then that can be given here as if you look into this, A double dash and A double dash is a stretched view of the plane A dash and A dash, and so now the total stress when it is applied, so it is apportioned between the intergranular stresses, that is the stresses which are taken by the grains or solids in the soil mass plus water. So, now AC is the area occupied by the solids and AW is the area occupied by the water. That means that the difference of total area minus area of contact is the area of water, which is the pore water area. So, wavy plane A dash and A dash passes through the particle to particle contact points, almost entire plane passes through pore water, because especially for granular soils, if the contact areas are very less, it always tries to pass through entire pore water. So, if you look into here, we have got a force F dash which is merely acting on the solid grains at the contact points, and UW which is acting in the pore water, that is on the inner surfaces of the solid grains. So, let us look the static equilibrium of this particular condition. So, since the soil element is in equilibrium, that is what we have considered, the algebraic sum of the forces must be equal to 0. So, let us consider a summation of vertical forces sigma mv, sigma fv is equal to 0. So, here if I do that, so I am having 3 forces. One is sigma A, that is total stress acting over an area, imaginary area A, over which this entire total stress is acting. So, area A is the one which is resulted due to the stretched view or a stretched plane of A dash and A dash, which is passing through the contact points. So, sigma A is the total stress on the account of overburden, sigma multiplied by the area of the plane A. So, that is the one force which is acting downwards, and UW is the pore water pressure multiplied by the area of the plane which passes through pore water AW. So, UW is the total force resulting due to the pore water pressure in which is acting over in the area of voids. Now, that is nothing but area of voids is nothing but area of water. F dash is the summation of forces which act at particle to particle contacts through which the plane passes. So, F dash is the summation of the forces, which act at particle to particle contacts through which the plane passes. So, now let us consider the static equilibrium in the vertical direction. So, from this applying the laws of statics to soil element in equilibrium, AC plus AW, that is area of contact plus area of portion which is occupied by the water, AW, is equal to total area A, that is the area of the plane. So, here this can be written like this: sigma A is equal to F dash plus UW into AW. So, by dividing with A dash, this can be written as by dividing by A, this can be written as sigma is equal to F dash by A plus UW into A minus AC by A. So, this can be simplified like sigma is equal to sigma dash plus UW into 1 minus AC by A. So, AC by A is, if you write like A, where A is the contact area between particles per unit gross area of the soil, then this can be reduced to sigma is equal to sigma dash plus 1 minus small a into UW. So, for granular materials, for granular materials, A, that is this contact area between particles per unit gross area of the soil, tends to become to 0. In that case, here this works out to be sigma is equal to sigma dash plus UW. So, for the granular materials, when the A tends to 0, then sigma is equal to sigma dash plus UW. So, from this deliberation, from the spring analogy, we have proved that sigma is equal to sigma dash plus UW. So, from this, applying the law of statics in the considering for the equilibrium in a saturated soil mass, we have deduced an equation called sigma is equal to sigma dash plus UW, where sigma is the total stress, sigma dash is the effective stress, and UW is the pore water pressure. So, if you look into this in this slide further, the effective stress is not the stress at particle to particle contact. So, this effective stress is not the stress acting at particle to particle contact, that is required to be noted. This is acting over an imaginary area A, passing through pore water as well as passing through solids as well as some contact points. So, stress at particle contact is a physical stress equal to F dash by AC. So, it will be very high because of the sometimes minute contact areas can induce very high contact stresses. So, here in this slide we try to apply the laws of statics to soil element in equilibrium, and then we have deduced total stress is equal to effective stress plus pore water pressure. So, we can say from this slide and the previous discussion, in a saturated soil, therefore, effective stresses may be viewed as force transmitted at particle to particle contacts divided by the area of the wavy plane that passes through these particle contacts. So, here the effective stress equation is given in a pictorial representation, where here sigma dash which is resulted due to the grain to grain interaction over an area A. So, area A is the area of this mold, cross section area of the mold perpendicular to the application of the stress, and U is the pore water pressure. So, sigma dash plus UW is equal to sigma, that is the total stress. So, what we have derived is that total stress is equal to effective stress plus pore water pressure. Now, let us consider once again at point O in this particular location a strata or having a saturated soil, and XX is the wavy plane passing through the contact points. So, if you look into this diagram, see here F1, F2, F3, F4, so on to Fn are the forces acting at the contact points. So, through this wavy plane, if I draw and this passing through the contact points, it results like this. So, let us consider at this particular level, if I stretch this, then imaginary plane results that can be called as say XX, and here if I look into the computation of the total stresses and pore water pressures at this case, with this example we can see. So, H2 is the height of soil mass, saturated soil mass above point O. So, point O is located here, and H1 is the dry soil unit weight, which is having gamma as the dry unit weight. So, water table is located H1 meters below this ground surface, and So, here the pore water pressure is, if I put a standpipe here, the water will rise under hydrostatic conditions up to H2. That is, H2 is the height that indicates that the pore water pressure at this point is gamma W H2. So, here if I look into this is the total imaginary area passing through the plane XX perpendicular to the application of the stress resulting due to war burden in this case. Then area of the contact soil solid is somewhere here, area of the contact soil solid is here, and total area of the contact soil solid is AC. So, A minus AC, that is nothing but AW, which is again is taken over by water, which is filled with water. So, here at point O we can write total stress as gamma H1. In principle, it is gamma D H1, gamma suffix D, that is the dry unit weight of soil mass. Here gamma D is equal to gamma. So, gamma H1, H1 is the height of the dry soil, and gamma sat, that is saturated soil mass unit weight, into H2. So, this is the total stress acting at point O. Pore water pressure at point O is gamma W H2. So, here the pressure is 0 and here the pressure is gamma W H2. So, the pore water pressure is gamma W H2 at this point O. So, effective stress is nothing but, now it is sigma minus UW. So, we can obtain like gamma H1 plus gamma sub H2. So, gamma sub is nothing but gamma dash is equal to gamma sat minus gamma W. So, that can be simplified and can be written as sigma dash is equal to gamma H1 plus gamma sub H2. So, let us look further into a fundamental difference of intergranular stress and effective stress by considering this particular diagram which is given in this slide. Effective stress is sometimes used interchangeably with intergranular stress. Although the terms are same and yield same meaning, but there is some difference that we will try to look into through these two slides. Now, let us look the total vertical force F at the level of O is the sum of the following forces, like forces can be like forces which are acting at grain to grain contact points, and forces which are resulting due to water, air, which can be some attractive forces or some repulsive forces which can happen in soils, particularly in clayey soils. So, if you see here, the forces carried by soil solids at their point of contact, say if I call that force as F solids, F solids is equal to F1V, F2V, F3V summation. That means that Fs is equal to F1V plus F2V plus F3V, so on. So, this F1V, F2V or F3V are the vertical components of F1 and F2. That means, if you go to the previous slide, here if you see here at the contact points you have got forces F1 and F2, F3 are acting. So, the vertical components of this F1 is F1V and vertical components of F2 is F2V, and vertical component of F3 force is F3V. Force carried by water. So, that force carried by water is nothing but UW into A minus AC. So, A is the total area of the plane under consideration and AC is the contact area. So, now FW is equal to UW into A minus AC. Then electrical attractive force between solid particles of the level of O, that is FA is the electrical attractive force between the solid particles of the level of O, and electrical repulsive force between solid particles of the level of O is FR. So, we have got the total forces is a summation of these forces. So, we can write now total vertical force F is equal to Fs plus Fw minus Fa plus Fr. Keeping view of the sign convention, the negative sign for Fa was given. So, F is equal to Fs plus Fw minus Fa plus Fr. Now, by dividing with area A, that is A is that imaginary plane area passing through that level point O in the previous slide, sigma is equal to sigma Ig, that is nothing but Fs by A plus UW into 1 minus AC by A minus A dash plus R dash, where A dash and R dash are the electrical attractive force and repulsive forces per unit area of the cross section of the solid. So, sigma Ig is intergranular stress, A is AC by A, and A dash is the electrical attractive force per unit area of cross section of soil, R dash is the electrical repulsive force per unit area of the cross section of soil. So, this can be simplified further by writing like this: sigma is equal to sigma Ig plus UW into 1 minus A dash plus R dash. So, here this is that now sigma is equal to sigma Ig plus UW into 1 minus A dash plus R dash. So, this when you discuss further, when you write in terms of intergranular stress, we can write like sigma Iz is equal to sigma minus UW into 1 minus A plus A dash minus R dash. So, the value of A is very small in the working stress ranges. So, A tends to 0 basically for granular soils. So, we can write like sigma Ig is equal to sigma minus UW plus A dash minus R dash. So, the value of A is very small in the working stress range. So, A tends to 0. So, in that case sigma Ig is equal to sigma minus UW plus A dash minus R dash. So, for granular soils like sands and gravels and silts and clays of low plasticity, or that means clays of low plasticity indicates that lean clays, the magnitude of A dash and R dash are small. And for all practical purposes, the intergranular stress becomes now sigma Ig is equal to sigma minus UW. So, here for granular soils, silts and clays of low plasticity, the magnitude of A dash minus R dash, the difference between A dash and R dash is negligible. So, we can write sigma intergranular stress, which is nothing but effective stress, is equal to sigma minus the pore water pressure. So, this particular deliberation we are discussing to look into this difference of the two terminologies for effective stress called effective stress and intergranular stress. Consequently, for in case of a highly plastic soils and dispersed clays, the A dash and R dash, that is attractive and repulsive processes, are very large. Depending upon the environment under which this deposition is taking place, it can be said that A dash minus R dash is very large. In such situations, we cannot say that intergranular stress is equal to sigma minus UW, because the contribution of A dash minus R dash will be there. So, here if you consider in this slide, we have got clay particles which are represented as a platelet particles and surrounded by the double layer water, electrical double layer water adsorbable layer, and then this water surrounding the soil particles. So, the clay particles and adsorbable water is shown here. So, depending upon the deposition and availability of the concentration of the salts, it can be this type of arrangement can be there, like face to edge and edge to face orientation. So, in the clay soils, mineral crystals are not in direct contact since they are surrounded by the adsorbed layers of water. So, the mineral crystals are not directly in contact to generate the stresses, but they are they mobilize along with in tune with the adsorbed water surrounding the platelet particles. It is assumed that intergranular forces can be transmitted through adsorbed water. It is assumed that in this case, particular case in the clay soils where this difference of A dash minus R dash is very large, so this type of arrangement is possible. In that case, it is assumed that intergranular forces can be transmitted through adsorbed water. So, intergranular stress for the case of sands and gravels and clays of low plasticity, we can say sigma Ig is equal to sigma dash is equal to sigma minus UW, whereas in case of highly plastic and dispersed clays where A dash minus R dash is very large, in that case we cannot really say sigma Ig is equal to sigma dash is equal to sigma minus UW, because of the large contribution of the A dash minus R dash, that is attractive forces, difference of attractive forces and repulsive forces acting over an area, cross section area of the soil. So, we have discussed as of now this saturated soil conditions, effective stress under saturated soil conditions, and we said that effective stress is equal to sigma minus UW. But as we discussed earlier, we have situations like partially saturated soils above the groundwater table. In such situations, how we define effective stress? Let us look through this slide. So, partially saturated soils exist in a three-phase state: air, water and solids. The water in the voids is not continuous because it is intermittently disturbed by presence of the pore air. Pore air occupies considerable volume in the system. So, here in this slide, grains are shown and water surrounding the grains are shown, and then in between the trapped air can be seen, that is the pore air pressure. So, in such situations we cannot say that the equation which was proposed like sigma dash is equal to sigma minus uw is valid. So, in that situations, total stress at any point is equal to effective stress plus pore air pressure plus pore water pressure. So, in these situations like total stress at any point is equal to effective stress, that is which is mobilized in the form of a interaction from the grains, plus pore air, that is when the air is under the pressure. So, pore air pressure and pore water pressure. So, this was discussed and then proposed by Bishop 1960. According to Bishop's 1960, we can say sigma is equal to sigma dash, that is effective stress, plus UA, that is pore air pressure, minus psi, a constant or a fraction of which is the fraction of the unit cross sectional area of the soil occupied by the water. So, psi is the constant and which is the fraction of the unit cross sectional area of soil occupied by the water into UA minus UW. So, this value of this psi is equal to 0 for dry soils. Then when the degree of saturation is equal to 0, then you can see that when this is 0, then sigma is equal to sigma dash plus UA, that is total stress is equal to effective stress plus pore air pressure. In case of saturated soil, when the psi is equal to 1, this reduces to that is with the degree of saturation 100%, sigma is equal to sigma dash plus UW, that is pore water pressure. For intermediate values of SR, psi can be read from the chart based on the triaxial tests on unsaturated soil samples. Bishop 1960 has proposed variation of psi with degree of saturation. So, this can be determined by the nature of the variation of psi with SR for several soils based on the triaxial tests on unsaturated soil specimens. So, this chart or this graph shows the variation of psi, a fraction is a constant with the degree of saturation. So, you can see here for 100% saturation this value tends to 1, and for this here 30% saturation the value works out to be around 0.4 or so. So, for intermediate partially saturated conditions this can be value can be obtained to compute the this total stress is equal to effective stress plus pore air pressure plus pore water pressure. So, having seen the definitions of effective stress for saturated soil conditions and then derivations based on these effective stress conditions, let us look into some applications like effect of water table on effective stress. So, water table at ground level, that means that here it is shown in this slide that soil surface, and gamma sat is the saturated unit weight of soil mass, and sigma dash is that effective stress, that vertical effective stress under consideration, and the small element which is shown there, and here is the water table level at the, in this particular case water table is located at the ground surface. So, pore water pressure at any depth is hydrostatic. So, at depth z, sigma v is equal to gamma sat z, because here at depth z we are interested in computing the vertical total vertical stress. Sigma v is equal to gamma sat z. UW, that is pore water pressure at depth z from the groundwater table. At groundwater table level it is 0, and then at depth z it is gamma w z. So, effective stress is equal to sigma v minus uw, which can be given as sigma v dash is equal to gamma dash z, where gamma dash is the submerged unit weight of soil or bionant unit weight of soil, which is nothing but difference of gamma sat minus gamma w. Another case like water table above ground level. Now, previous case we have seen water table at ground surface, now water table above ground level. Now, consider in this slide the water table ZW located above the ground level. That is, this is the ground surface. So, ZW is the water table located above the ground surface. So, when we interest now to compute total stress is nothing but gamma sat Z plus gamma W ZW, and UW is equal to gamma W into Z plus ZW. So, effective stress, when you simplify and write it like sigma V minus UW, and it is nothing but sigma V dash is equal to gamma dash Z. So, if you look into it, in the previous case when the water table is located at the ground level, we have got effective stress as gamma dash Z is independent of the that location of the water table. For example, if it is at the ground surface, we have got sigma V dash is equal to gamma dash Z. In this case, even with water table above the ground surface, the effective stress remains unchanged. So, effective stress is unaffected by water level above the ground surface. If the as long as the water table is located above the ground surface, the effective stress remains unchanged. So, let us consider this example, water table above ground level. In this example, gamma sat, which is taken as 18 kilonewton per meter cube, and gamma W is taken as 10 kilonewton per meter cube, and at depth Z is equal to 3 meters, ZW is equal to 2 meters. So, this is the cross section which is shown here of the profile. Now, water table above ground level, if you look into it, so sigma V is equal to 74 kilonewton per meter square, and pore water pressure at depth 3 meters below the ground level, and along with 2 meter height of water above the ground level, it is around 50 kg per meter square. So, the effective stress is around 24 kilonewton per meter square. So, this is the distribution of the total stress with the depth. This is because of the unit weight of the water. So, the slope of this particular line is different, and here is because of the slope is having different it is having different slope because of the saturated soil unit weight. So, this is the pore water pressure, and this is the effective stress, which is nothing but total stress minus pore water pressure. So, it gives us effective stress is 0 at this point, and effective stress at this point is sigma V dash is equal to 24 kilonewton per meter square. Let us consider another example like water table above the ground level, where this ZW is something like 2 kilometers or 2000 meters, representing some deep sea sediment bed. In that case, let us look how it changes. If you see here, total stress is increased by that equivalent amount. For example, gamma W is ZW is the one which changed. So, 20,054 kN per meter square is the total stress, and pore water pressure is 20,030 kN per meter square. The difference sigma V dash, if you see here, even in the case of deep sea sediments where the effective stress remains unchanged here. So, effective stress is unaffected by water level above the ground surface. This is just to demonstrate in case of estuaries and then deep sea sediment, estuarine bed and deep sea sediments. So, as long as the water table is above ground level, if it fluctuates, then effective stress remains unchanged. So, this is that distribution which is shown for the problem what we considered in example 2, where this ZW is equal to 2000 meters. So, this is the total stress, and this is the pore water pressure, and then 24 kilonewton per meter square is the effective stress. So, this tells us that effective stress in a submerged soil mass is independent of the depth of the water. So, effective stress in a submerged soil mass is independent of the depth of the water. Now, let us consider the fluctuations of water table within the groundwater table, within the ground level. So, this is possible every year because of the onset before monsoon and after monsoons, or during rain, or immediately after the rain, and after some time from the heavy rainfall. So, these fluctuations are possible. Also, the fluctuations of groundwater table also plausible because of the depletion of water table, because of the construction activities or dewatering of the this groundwater table and all. So, let us consider a saturated soil mass of thickness h, and the height of water table above the ground surface is say h1. This h1 is resulted due to say during heavy rain, the water table rose from ground surface to a height h1. So, this level 1 represents the initial water table location at ground surface, and 2 is the water level location during rain, that is water level rises because of the incessant rain. So, let us see how this can change the effective stresses. If you look into it, the effect of fluctuations of water table and effective stress we are discussing at level 1, that is initial water table at the ground surface. So, before rain, sigma V is equal to gamma sat H and UW is equal to gamma WH. So, sigma V dash is equal to gamma sub H or gamma dash H, which is the effective stress before rain. And this water level location has changed because of the during rain there is an increase in height of water level and rose from ground surface to height H1 to go up to level 2. Okay. So, 2 is the water level location. In this case, sigma V is equal to gamma sat H plus gamma WH1 and UW is equal to gamma W into H1 plus H. So, sigma V dash is equal to gamma sub H or gamma dash H. So, the rise of water level above ground surface increased both UW and sigma by the same amount, and consequently the effective stress remains changed. So, because of the rise of water table above the ground surface, both total stress and pore water pressure, the magnitudes have increased by the same amount. So, because of this the effective stress remains unaltered. Let us now assume that fluctuations of water table within the ground surface, like it can rise during monsoons, or it can deplete because of any construction activity, because of the dewatering of the groundwater table which is taking place, or depletion of the water table. So, in this case let us consider same soil profile, where here total thickness of the soil here is now H1 and initially the groundwater table is at the ground surface. Now, it dropped down to level 2 by H1 meters below the ground surface. So, H minus H1 is the saturated soil, and this can be dry or partially saturated, or it can be completely saturated depending upon the gradation and particle size and then pore spaces. So, that we will be discussing in the next lecture. But here 1 and 1 is the initial water level location, that is at the ground surface, and 2 and 2 is the water level after rain, that is after a rain, in the sense after long time after rain. So, depletion of the water table can take place, because during the water table can rise and it can affect the effective stress. Now, in this case what we are discussing is that after a long time after heavy rain, so there will be a depletion of water table. So, 1 and 1 the initial water level location before rain. So, as we discussed earlier, the sigma V dash is equal to gamma dash into H, but for this case when the water table drops down by H1 meters below the ground surface, then if you see the sigma V is equal to gamma D H1, assuming that the soil above that new groundwater table level, that is 2 is say dry, then gamma D H1 plus gamma sat into H minus H1. So, UW is equal to gamma W into H minus H1, because now the groundwater table is from is H1 meters below the ground surface. So, the pore water pressure at depth H below the ground surface, that is from the groundwater table, is gamma W into H minus H1. Now, if I look into the difference of this sigma V minus UW, definitely the sigma V dash is greater than sigma V dash which you computed for location of water table at the ground surface. So, this indicates that when the water table drops down below the within the ground surface, there is a chance of increase in the effective stress. So, sudden depletion of water table causes increase in the effective stress, but this transfer of effective stress is something like is not an instantaneous phenomena. It depends upon, for clays where the water flows very slowly, it takes long time. For sands, it can occur rapidly. So, and could lead to, in case with when there is a sudden depletion of water table and causes increase in effective stress, when this is happening all of a sudden, then could lead to the crushing of the grains, because increase in effective stress can put this contrast stresses very high. So, this can lead to the crushing of the grains, and crushing of the grains is nothing but readjustment of the soil particles, nothing but volume change, or resulting into some settlement of a structure or a collapse which can take place. So, this particular case, when the water table depletes, then we have shown that the effective stress can increase. Similarly, within the ground surface, now if the water table increases, what it happens is that this effective stress decreases. So, a case like when the water table rises within the ground surface, then there is a chance of increase in the decrease in the effective stress. So, effect of fluctuations of water table on effective stress. With a shift in the water table, there is a change in the distribution of pore water pressure with depth occurs over a finite time interval. So, this finite time interval varies from type of soil. Time interval is long in soils like clays, in which water flows slowly, and almost instantaneous in soils like sand, in which water flows very fast. Why the water flows very rapidly in sands and why it is slowly in clay, that we will be discussing later. But at this point, we can take like time interval is long in soils like clays, in which water flows slowly, and almost instantaneous soils like sand, in which water flows very fast. So, when pore water pressure are adjusting to the new location of groundwater table, the conditions of water can be described as being transient hydrodynamic. When this is water table fluctuations are taking place, when this the adjustment to the new water table is being taken place in the soil mass, so those conditions are called transient hydrodynamic conditions. After achieving equilibrium condition, it changes to hydrostatic again. So, when pore water pressures are adjusting to the new location of the groundwater table, the condition of water can be described as being transient hydrodynamic. So, we can summarize that effect of water table on the fluctuations of water table on the effective stress. If you say, if you summarize, then we can say, like for water table below ground surface, a rise of water table causes a reduction in the effective stress, and a fall in the water table produces an increase in the effective stress. That means that we have seen a case like fall. If you consider a case like rise of water table within the ground surface, you will observe that effective stress decreases. So, for water table above ground surface, a fluctuation in the exposed water level does not alter the effective stress in the soil. For water table above the ground surface, if the water table rises from 2 meters to 200 meters to 2000 meters, as it is independent of the depth of the water. So, the flow for the water table above the ground surface, a fluctuation in the exposed water level does not alter the effective stress in the soil. So, these two conclusions, like the variation of the groundwater table within the ground surface, like when it drops, then there will be an increase in effective stress. When it rises, because at the onset of monsoons the water table can rise, that leads to a decrease in the effective stresses. So, let us consider some facts noted each year during monsoon through personal observations or newspaper reports. Like during monsoon, we always see that the groundwater table is known to rise, and hence the effective stress reduces. That is what we have discussed in the previous slide and we have summarized. And so does the shear strength. What will happen is that when the effective stress reduces, then that means that the grains are being deprived from generating these contact stresses. So, with that actually the shear strength reduces. The more details we will be learning in the due course of our lectures, but here the shear strength decreases. When shear strength reduces below the magnitude of the shear stresses in soil, so there is some the stresses which are there to support the textural load which is created in the form of a total stress. Then when shear strength reduces below the magnitude of the shear stresses in soil, then soil slides and collapses occur. So, increase in sigma occurs instantaneously. So, one thing which we should note is that increase in total stress sigma occurs instantaneously, whereas increase in effective stress is not instantaneous. Since particle adjustment and readjustment is not instantaneous. Since the particle adjustment and readjustment is not instantaneous, so we can say this effective stress, change in effective stress is not an instantaneous phenomena. Whereas in case of total stress, which is resulting either due to the accumulation of water above the ground surface, or due to the man-made activities like construction of fields or construction of structure, wide area of fields or accumulation of the ground, can change the total stress, which is an instantaneous phenomenon. So, increase in effective stress occurs instantaneously, whereas an increase in effective stress is not instantaneous, since particle adjustment and readjustable particles depend upon the type of the soil it takes place. Now, as we discussed in the previous lecture, we said that pore water pressure has got another terminology, another term called neutral stress or neutral pressure. Why that is called, a pore water pressure is called neutral stress or neutral pressure? Let us look through these two slides. Consider a soil mass of certain thickness and assume that this is the surface before placing lead balls. So, here the lead balls are loaded on the soil mass such a way that they induce a vertical stress sigma. So, surface of the soil mass after placing lead balls, that means depleted here. So, change down to height h, small h, it got settled. So, the void ratio, because of this, the void ratio changes from E naught to E1. E naught is the initial void ratio before placing the lead balls with an intensity sigma, and E1 is the void ratio which is resulted because of the after placing lead balls. So, E naught to E1 produces a change in other mechanical properties of it. So, change in void ratio means change in other properties of the mechanical properties of the soil. So, for this reason, because here the soil being dry, whatever the total stress which is applied sigma is equal to sigma dash, because UW is equal to 0. So, we can say that for this reason, when this effective stress can induce changes in the volume in the form of the changes in the void ratio. So, that is the reason why the effective stress is called effective stress, we have discussed in the previous class. So, only the effective stress can induce changes in the volume in a soil mass and can produce frictional resistance in the form of changes which can be produced. Contrary to this, for example, if the same mold which is filled with same soil, but is subjected to water level of equivalent to the height equivalent to the stress intensity given by these lead balls. So, let us consider here, suppose if I consider same soil, but it is saturated, and then this height of the water level is maintained such a way that HW is equal to sigma by gamma W. So, if I do this, then what will happen is that increase in pressure due to the weight of water does not have a measurable influence on the void ratio or any other mechanical property. Therefore, the pressure produced by the water is also called as neutral pressure or neutral stress. So, neutral stress cannot by themselves cause volume change or produce frictional resistance. So, neutral stress, that is water pressure which is acting on the voids of the soil, cannot by themselves cannot produce any volume change. So, when there is no volume change, then there is no change in the properties of the soil mass. So, in keeping this point in view, generally this pore water pressure is also called as neutral stress. So, here in this slide what we have seen is that same saturated the soil mass which is saturated is subjected to a stress intensity equivalent to sigma by gamma W, where sigma is the stress intensity which we have given in the previous slide to the dry solid soil mass. Then we said that sigma is equal to sigma dash. Because of this placement of the lead balls, there is a change in void ratio, that is void ratio, decrease in void ratio E naught minus E1 induces some change in the mechanical properties of the soil that can change the shearing resistance. So, here in this case, if it is subjected to equivalent stress as that in the previous case, but the increase in pressure due to the weight of the water does not have a measurable influence on the void ratio or any other property. So, the properties remain unchanged. When the properties remain unchanged by virtue of this water pressure, because this neutral pressure cannot by themselves cause volume change or produce any frictional resistance. Because of this pore water pressure is also called as neutral stress. So, in this lecture we try to understand about the concept of the effective stress, and then we try to discuss about this fluctuations of water table above the ground surface, and we have summarized that as long as the water table maintains level above ground surface, even if it changes its level above ground surface, something like example like 2000 meters, that means 2 kilometers above the ground surface, like in deep sea sediments, does not alter the effective stress remains unaltered. Because here the change in total stress and pore water pressure occurred by the same amount. Because of this, the effective stress remains unchanged, because we said that the effective stress is equal to total stress minus pore water pressure. Contrary to this, if the water table fluctuates within the ground surface, that is, if there is a depletion of water table, if there is a drop in the water table, say after heavy rain, then there is a chance of increase in effective stress. But increase in effective stress is not an instantaneous phenomena. It occurs over a finite interval of time. It depends upon the type of the soil. For soils like sands, where the water flows quickly, then these changes can occur rapidly. Whereas in case of clays, then we said that it can occur over a period of time. Whereas total stress and total stress is changed because of the it is an instantaneous phenomena. Then we discussed that when the water table rises within the ground level, then there is a decrease in the effective stress. So these two important discussions we made, and then we also discussed some examples like water table at the ground surface and water table variation within the ground surface. Then we try to understand this concept of the effective stress through examples. Then afterwards, we have defined the difference between or terminologies like effective stress and intergranular stress. Then we also try to discuss about the another name of pore water pressure, which is popularly known as, for the pore water pressure, also called as neutral stress. So that is discussed, and through a simple example, then why the neutral stress is called pore water pressure we have introduced, and then we try to discuss.